Hi everybody, today we're going to talk about exponentials. So we need to start by saying, well, what is an exponential? And basically we're going to look at exponential functions, but what I think you're used to hearing is the word viral, which means something spread really quick. So think about videos on TikTok or posts on Instagram, things that just spread to a lot of people in a short amount of time. That's what we call a viral video. But I also want to make sure that we understand the difference between a line and an exponential. A line's pretty consistent. It does the same thing over and over again. So if we looked at this line, y equals 2x, and we change it into a table, you can see that the values of the y are increasing by 2. It goes from -4 to -2, -2 to 0, 0 to 2, 2 to 4. So every time we move from point to point, we increase the y value by 2. Now if I change and I add a value, if I put in the function y equals 2 to the x, I get a curve. In this curve, things are not moving consistently. You can see it's really close to 0, it's moving up, and then it's jumping. And as I pull back the graph, you can see the values get higher and higher and higher the more we go. Again, if I say let's add in a table, you can see that there's not a consistent number that's increasing by. It went from 0.25 to 0.5, 0.5 to 1, 1 to 2, 2 to 4. If I continue and put in 3, 4, 5, 6, you can see the values jumping. So what's happening? We're multiplying by a value of 2. Let me show you that in the real world. So I think we're all used to this now. These are COVID cases, and this is from Our World in Data. And you can see there are two things going on here. There is this blue curvy thing, right? And that represents the total confirmed cases of COVID in the United States versus the line along the bottom, which represents total deaths. So you can see the line increases by about the same amount from day to day, month to month, and unfortunately now we're becoming year to year, where the number of confirmed cases is jumping, right? So that's more exponential. This exponential is a little more complicated. It's kind of like there was an exponential, it slowed down, there's an exponential. An exponential function can be written as f of x equals a times b to the x, where b is greater than 0 and not equal to 1. A is what we're starting with, so we're going to call that the initial amount. And b is the growth or decay rate. So sometimes things are getting bigger, sometimes things are getting smaller. How we can tell if something's growing or decaying is by looking at the value of b. When b is bigger than 1, b minus 1 is the growth rate. If b is between 0 and 1, 1 minus b is the decay rate. That says anytime b is bigger than 1, we know it's growing. Anytime b is less than 1, we know it's decaying. We'll get to the growth and decay rate in just a minute. So let's try this. We're going to find the rate of growth for each of these exponential equations. We'll say what the initial value is, what the growth or decay is, and then what the rate is. So let's start with y equals 42 times 1.5 to the x. The initial value is 42. Because 1.5 is bigger than 1, I know this is a growth. And then to get the rate, we do 1.5 minus 1, which is 0.5. Let's write that as 50%. The next one, y equals 5,000 times 0.85 to the x. Our initial amount is 5,000. 0.85 is less than 1, which says this is decaying. And then to get the rate, we have to do 1 minus 0.85, which is 0.15. We can write that as 15%. The next one, y equals 325 times 1.04 to the x. We start with 325. 1.04 is bigger than 1, so that's a growth. Then to get the rate, I do 1.04 minus 1, which is 0.04, which says that's 4%. Y equals 89 times 0.72 to the x says we're starting with 89. 0.72 is less than 1, so that's a decay. And then the rate is 1 minus 0.72, which is 0.28, or 28%. The last one, y equals 1.14 to the x. Now notice, the initial value, we don't see a number in front of the 1 times 1.4 to the x. That means the initial value was 1. And then what is it doing? It's growing, so we're going to say that's a growth. Then to get the growth rate, we do 1.14 minus 1, which is 0.14, which becomes 14%. Well, let's look at some applications. According to Forbes, the Maserati quadruport was the fastest depreciating car of 2020. The value of the car can be modeled by V of t is 126,990 times 0.7387 to the t, where t is the number of years after it was purchased. We're going to first find the initial value and then find the decay rate. So the initial value is the purchase price of the car, $126,990. Remember the decay rate. 0.7387 is less than 1, so we know it's decaying, and we need to do 1 minus 0.7387. This gives me 0.2613, which is 26.13%. I like this application because we can get a better feel for what it means to depreciate and what a decay rate means. So this says the car is losing 26.13% of its value every year, and it's retaining the 73.87. So it's going to keep 73.87% and it's going to lose 26.13%. This is not an investment. So now, keeping that, we're going to find the value V of 1 and then V of 2. We're going to put in 126,990 times 0.7387 to the power 1. This says after 1 year, the car is now worth $93,807.51. Now let's look at 2 years. So we go back to the beginning, 126,990, and we put 0.7387 now squared. This is $69,295.61. That's a huge amount of depreciation for just 2 years. Let's look at something that doesn't change as quickly. So also according to Forbes, the Jeep Wrangler is the slowest depreciating car in 2020. The value of the car can be modeled by V of t is 35,820 times 0.93 to the t, where t is the number of years after it was purchased. We're going to find the initial value of the car, and then we're going to find the decay rate. So the initial value of the car is $35,820. Again, this is decaying because that 0.93 is less than 1, so the decay rate is 1 minus 0.93, which is 0.07. This is a 7% decay rate. So we see it's retaining 93% and it's losing 7%. A big difference from our first example. So this time we're going to find V of 2 and V of 5. So we're going to see what's the value of the Jeep after 2 years, what's the value of the Jeep after 5 years. In 2 years, I have 35,820 times 0.93 squared. This is $30,980.72. So it went down not quite $5,000. And then V of 5, we have 35,820 times 0.93 to the fifth, which gives us $24,919.56. Still not an investment, but not depreciating as quickly because the decay rate was much smaller. Let's work on writing some exponential equations. So in this chart, I've given us initial values. I've told you if we had a growth or a decay, and then we're going to write the equation. The first one says the initial value is 38, the growth rate is 10%, and we're going to write the equation. So we're going to write y equals 38. Remember, we need to add this 10% to 1, so 1 plus 0.10 is 1.1, and then to the power x. The next one says decay. So we have 12,950 as our initial, so I'm going to write 12,950. Because it's decay, we're going to subtract from 1. 1 minus 0.14 is 0.86, so we have 0.86 to the x. Our third one says 342 as our initial value, a growth rate of 150%. So let's start with y equals 342. Well, remember, when we make it a percent, we're kind of moving the decimal place over 2, so this becomes 1.5. We do 1 plus 1.5, that's 2.5. So I have 2.5 to the x. This is a big growth, probably bigger than you're usually thinking, but you do hear things grew 150%, 200%. It's okay to grow more than 100%. The next one says, initial value of 87, a decay rate of 4.5%. We're going to write y equals 87. We're going to do 1 minus 0.045, which is 0.995. So I have y equals 87 times 0.995 to the x. Then the last one, initial value is 105, a growth rate of 0.1%. We have y equals 105. times. Remember, we're going to add, but be careful with this 0.1%. 0.1% means 0.001. So 1 plus 0.001 is 1.001. This is our growth rate. So 105 times 1.001 to the x. This one particularly I do think of as an application of, think of your savings account. If you look at your savings account, the amount of interest is very, very small, often 0.1%. So I thought, why not express that as something that we can talk about as something that's growing? So let's take some more examples now and take some word problems and turn them into some equations. So I looked up that in ideal conditions, E. coli grows at a rate of 3.526% per minute. And notice that I did say per minute, so this is really quickly. If a population starts with 25 E. coli, how many will be present in 45 minutes? We want to start by writing our equation. So we're going to write y equals, our initial amount was 25. Then we have a growth, so we're going to do 1 plus 0.03526, which is 1.03526. And then because I said this was time, I'm going to write a t this time, but you could also write an x. We're going to say y is equal to 25 times 1.03526, and then we had 45 minutes that passed. This gives me y equals 118.895, or we could just go ahead and round that up to 119. So you can see here's something exponential. This says I started at 25, and 45 minutes I have 119 bacteria. This should be enough to give you pause and think, don't leave things out on your counter. They need to go in the refrigerator when you're done with them. The population in Nevada was 3.1 million in 2020 and is growing at a rate of 1.5%. Let's write an equation for the population, and then we're going to use that to model the population in 2024. So to start with, we're going to write y is equal to, I'm leaving it as 3.1. I'm not going to write all the zeros after it. We're just going to know whatever answer we get out will be in millions. And then this is a growth rate, so I have 1 plus 0.015. So this is times 1.015. And again, I'll do t for time. Now we're going to look at what the population will be in 2024. Our time here is 2024 minus 2020. So our y is 3.1 times 1.015, and then this will be 4 years that it's passed, so there's our exponent of 4. I'm going to give our answer in 2 decimal places, so I have y is equal to 3.29, and let's just write the word million, so we're thinking about millions there. I also looked up things that are growing exponentially, and I found that U.S. tuition is one of them. So U.S. tuition for colleges and university increases on average at 3% a year. So if we had a particular university that had a tuition of $18,000 a year now, let's figure out what the tuition will be in 8 years. So we say y is equal to, we have our initial amount, $18,000. This is a growth. It's 3%, so you know what we're going to do. We're going to do 1 plus 0.03, which is 1.03, and then the time that's going by is 8 years. So this says in 8 years, the tuition will be $22,801.86. And finally today, we're going to do a comparison. So I have 2 apartments offering monthly rent for $1,485 per month. Apartment A states that rates will increase $50 a month each year, and Apartment B states the rates will increase by 3.3% each year. We're going to complete the table to determine which apartment is better for a long-term rental. So the first one, Apartment A, is a linear increase. It's going to go up by $50 each year that you stay. So we could write y is equal to 50x plus 1,485. Apartment B, though, is exponential. We have our initial value, 1,485. The 3.3% increase says we have 1.033 to the x. So we can see the 2 different ways these are growing. So if we want to plug in 1, plug in 2, plug in 3, plug in 4, plug in 5. But we have an easy way to do it. We can go to Desmos to get this done. So to start, I'm going to enter my 2 equations. I had 50x plus 1,485. Then apartment B was y equals 1485 times 1.033 to the x. To make this easier, we're going to change these to tables. So I'm going to go to the edit, I'm going to say make a table, and instead of the values it has, I'm going to type 1, 2, 3, 4, 5. Same thing for B. I'm going to change that to a table, and I'm going to go 1, 2, 3, 4, 5. So we can see these values, right? And we can compare year to year and see what's happening. In the first year, they look pretty equal. The second year, again, pretty equal. But then over time, we can see that the second one's getting bigger. So let's take these values, put them back into our chart so we can look at them year to year. Now I have the comparisons. Year 1, it goes up $15.35 for apartment A into $15.34.01 for apartment B. So it's slightly cheaper for apartment B. Same thing on year 2, $15.85 for apartment A and $15.84.63 for apartment B. Year 3 is where the change comes in and that B gets more expensive. So A was $16.35, B was $16.36.92. So it's about $2, but it's enough that you might think about it because that is per month. By year 4, apartment A is $16.85 and B is $16.90.94. And then in year 5, A is $17.35 and B is $17.46.74. So you can see it's getting larger and larger, that difference from year to year. Which one you would pick would probably be determined by what you think long-term means. So if long-term to you is 2 years, you would pick apartment B. If long-term to you is 4 or 5 years, you would want to go with apartment A.